So LLVM is the LLVM intermediate representation itself has qualities of a portable high-level assembly language, which is similar to high-level assembly language because it has constructions that map closely to system hardware, and it has backends for almost every system architecture. So it is a RISC-like instruction set, meaning that it has a limited set of platform-agnostic instructions. So although for Intel x64 includes many specialized instructions, they are not part of LLVM intermediate representation because adding new specialized instructions would break the binary compatibility of the bit code. So in that case, it is something like an abstract or not machine-specific assembly language. LLVM intermediate representation must also be able to represent high-level language constructs additionally. So it is in result neither very high level as in closely attached to the source language, nor very low level as in close to the target machine instructions. So as a platform-independent assembly language, ideally the LLVM intermediate representation should have been completely target-independent, but it is not so because of some inherent target independence of the programming language itself. That includes inline assembly code in high-level programming languages, and additionally, when using C standard headers in the Linux system, the header files are target-dependent, and then the bit width of the non-standard C data types depends on the underlying OS and architecture supports, and also it depends on padding and alignment instructors. It's also target-dependent. And then the system calls of the particular target architecture and OS are dependent. So that's just a little curious trivia of LLVM. But moving on, how does the LLVM compilation process work? In LLVM, we have two main forms of on-disk representation. We have human-readable source code files, and we have a bitcode file, which is a binary file format. So LLVM disassembles the bitcode files, giving you human-readable intermediate representation source code. And LLVM assembly assembles the source code files, giving you the bitcode format. We can also use opt tool to optimize each bitcode file individually. And then we use the LLVM linker to link together all the bitcode files into a single bitcode file, which we can then either execute using LLI, or we can use the LLC, the LLVM intermediate representation compiler, to compile the LLVM intermediate representation bitcode files into the target architecture's machine code executable file. So that's that. So here is a table of useful commands to know when working with LLVM intermediate representation. I'll just briefly go over them, but you can look at the slides later, so this is useful for just reference. But basically, we can check if a certain LLVM file is indeed valid syntax, and we can generate control flow graph for every function in LLVM intermediate representation. As mentioned, we can assemble, disassemble, and link intermediate representation source code files, as well as generate either bitcode files or LLVM intermediate representation source code files given a code file of a high-level programming language. Next, I will talk about the structure of the LLVM intermediate representation source code file, which is called a module.
So Sorry to interrupt. I just want to add to the previous slide that control flow graph generation is very useful in our debugging, especially when we are debugging very big shaders that have a lot of control flow structure. So yeah, I just want to add to that. The control flow graph generation is very useful from the OPIC
Yes.
tool.
And I will actually go over that later, maybe today if we have time. If not, maybe in the next session I will go over control flow graphs and how they look like for various control structures in more details. So this is the structure of the LLVM intermediate representation module. A module, it's a nested structure, a hierarchical structure, meaning that your module, which is your source code file, contains some target information and basically 0 or more global symbols. If you're familiar with regular expressions, that star at the end means 0 or more of the preceding data type. So we have global variables, function declarations, and function definitions, and inside the function definitions we have basic blocks. So this is our an example of a module file. We have target information first that tells us information about the target machine that we are compiling, including the various available data types and whatnot. We'll get to that later. Then we can have global variables. We have global function declarations, and then we can have function definitions, and we can have some other stuff. I'm not sure what this other stuff is. It's some kind of attributes that is automatically generated by Clang if you compile C code into LLVM intermediate representation code. But for now, we won't worry about that. So zooming into function definition, we see that it contains the definition, then the data type of the return, then the name of the function, and then it has 0 or more arguments. So each function must contain at least one entry basic block, which is the basic block into which execution of the function jumps. And then after the entry basic block, which is required, it contains some more optional basic blocks. So you can have functions with complicated control flow. Moving on to what is a basic block. Every basic block it contains some instructions, and every basic block ends with a terminator instruction, which transfers the control flow to a different basic block or to a different function. For example, we have two basic blocks here. About the target information, an intermediate representation module usually starts out with a pair of strings describing the target. Target data layout probably describes the layout of the data machine code in the final executable that will be generated. So the different fields are separated by dashes. And in this example, we can see it has information about little endian. Then for the main name angling, M:E denotes ELF type. We also have ABI alignment, which says that 64-bit integer is of 64 bits. Then we have the native integer width of the target data layout. And then the target triple, it describes the architecture. Then the vendor, so the producer of this machine, such as Apple, IBM, Intel, or Lenovo. In this case, we don't know who the vendor is. And then we have the operating system and the application binary interface. So we can, by looking at these two lines of code, we can gain some information about the host machine that the source code was compiled on. So for example, this one was compiled on an Apple PC running Mac OS X And then this table shows the possible values of each field in the target triple. So not all combinations of these four are valid, however. For example, some architectures do not support specific operating systems or AVIs. But this is just a table for reference of common values that you might encounter. So a question that you might have is, if I'm writing my own custom LLVM intermediate representation source code, what target information should I use? So my answer is the best way to find out the target strings would be just to take a simple C source file, compile it into LLVM intermediate representation, and copy paste those strings into your custom intermediate representation. So some basic principles of this programming language is like assembly code. It is a sequentially executing series of instructions. Its main property is single static assignment, which basically means that a variable can only be assigned to once, and once it is assigned, that value cannot be changed. A value is also an instruction, meaning that most instructions return values. As far as I know, the only way to get a value is the return value of an instruction as by the SSA property. However, there aren't exceptions. Some instructions do not return values. Specifically, terminated instructions do not return values, and also the store instruction does not return a value. Now, LLVM intermediate representation has an infinite number of registers. That leaves register allocation as a problem for the backend, which makes sense because different architectures have different numbers of registers. So, for example, embedded systems for ARM architecture generally have more registers than x86 desktop computers. Specifically about single static assignment. Since in single static assignment the variable can have only one assignment, we instantly know what its value is. Without single static assignment, the value of the variable depends on what line we are currently at, such as in C++. So intermediate representations which do not support strict static single assignment property depend on building a def use graph for doing analysis on the variables. And building a def use graph is computationally expensive. So by using the static single assignment property, prohibiting reassignment variables, it makes things simpler. So LLVM intermediate representation sacrifices space complexity, so it has more variables, in order to save on time complexity for determining data dependencies. So this is an example of a space versus time trade-off, which is very common in computer science. So that is why LLVM intermediate representation uses single static assignment property specifically. So next question would be, how does a compiler convert C code into LLVM intermediate representation? More generally speaking, how do you convert code not in single static assignment form into code in single static assignment form? So for example, what if each variable is assigned to twice? Then each assignment would become its own copy of the variable. So as you see in this example right here, because y is assigned to twice, they actually become entirely separate variable. And when that variable is used, we replace that use of the variable with the most recently created definition. Again, there only has been some limited amount of time for me to look into how LLVM intermediate representation is generated, but this is just the more basic concepts. So another interesting thing to note is the single static assignment used in LLVM intermediate representation is strongly typed. So you can expect to be told when you do something wrong with the data types. LLVM intermediate representation specifies the return type and the parameter types explicitly of a function, such as in this main function here, we explicitly specify all the return types. So being typed enables a number of optimizations to be performed on the intermediate representation directly. Another useful thing to note that is that LLVM intermediate representation does not differentiate between signed and unsigned integers, which we will go over later. What are the implications of that? So I just highlighted, but which data types do we explicitly provide? We explicitly provide data types of function parameters, data types of arguments that are passed into a function when you are calling that function. We specify the return types of functions in the declaration and the definition, and while calling the function also. And we specify the return type of the argument to the ret instruction, which has to match the return type in the definition. And we also specify the data types of arguments to instructions, such as this argument right here. All of them have explicit data types. Now, we have two different ways of representing programs. The first way of representing programs is the Clang AST, Abstract Syntax Tree. So the front end of a programming language uses an abstract syntax tree to model the structure of the source code. And it includes information about the high-level constructs of the programming language, which is better suited for representing high-level languages. And this information is generated from the parser. So it has information about the syntax and semantics of that high-level programming language, enabling the compiler to understand what the high-level code looks like. So it is specific to a certain high-level programming language. However, for the intermediate representation, we are using a different data structure called a control flow graph to model the behavior of the source code during the runtime. Control flow graph includes information about the control flow through different basic blocks, because we are now having a different programming paradigm. We are representing assembly code which lacks high-level constructs. And because we think of assembly code as a series of sequentially executing instructions inside of basic blocks instead of these complicated trees of nested expressions, we are using specifically the control flow graph data structure. Control flow graph is used in the middle end and in the back end also. So it's used for understanding how the code gets executed by the CPU and which basic blocks of instructions execute in what order. And the control flow graph, as you see in the diagram, it may also fork to express a control flow change, but it also merges nodes. For example, this will be a phi node, which we will get into somewhat later. So, about basic blocks, more detail. What are basic blocks? It's a list of sequentially executing instructions, starting with a label, which is the entry to the basic block. And then, after a list of those sequentially executing instructions, we are ending with a terminated instruction, which moves the control flow of the program to another basic block. For example, we can branch to a different label, another basic block, depending on a certain condition. we can, at the end of a function call, we can return to the calling function, and we can also have a switch statement which jumps execution to another basic block depending on the switch value. Basically, once the program enters the basic block, it will execute all the statements within that block sequentially until it reaches a terminator instruction, which transfers control flow to another basic block in the program. An interesting thing to notice is that a call instruction is not considered a terminator instruction, so that is a very common mistake by beginners. Now, why is a call instruction not considered a terminator instruction? It is because the program execution temporarily transfers to some function, but eventually it will return to the calling function and continue executing the statements in that basic block sequentially on down. So using debugger terminology, if we, for example, step over instead of step into the called function, it would appear as though the basic block keeps executing sequentially on down. So that is why the call instruction is not considered as a terminator instruction. However, it must be noted that any called function, it may exit the program without returning. Well, then we can't do anything about it. So another caveat of having each basic block always end with a terminator instruction is that there can be no fall through into the next basic block. Unlike labels in x86 assembly, or for example, Go labels in C++, you cannot just fall down the basic block. So, because the start of another basic block is limited by a label, if you put a label inside the basic block, that splits it up into two basic blocks. So if you want all codes to execute sequentially, you would have to put an explicit unconditional jump to the next basic block at the end of a previous basic block. So you have the following data types in LLVM intermediate representation. Basically, the difference between LLVM and C++ is that LLVM accepts arbitrary bit width for integer data types. So all of these three examples are valid code. You could have a 7-bit integer, or a 77-bit integer, or a 100-bit integer. Now that's cool and all, but although when linking together with code originally written in other programming languages, LLVM intermediate representation has to obey their conventions for bit widths of integer data types. So usually you would not see such data types pop up. Usually you would see data types in powers of 8, powers of 2, binary size data types. So in this table, there are some data types here that are very useful, such as I8 pointer. That's the analog of character pointer in C++. It is used for C strings. And then I8 pointer is used for specifying argv, the command line arguments. So that's a very useful thing to note. And then this half data type has no equivalent in C++. It's a 16-bit IEEE floating point value, but it's not used in most high-level programming languages. So we probably won't see it all that much if we are analyzing LLVM intermediate representation code that has been compiled from a higher-level programming language. Another thing is that some high-level programming languages, such as Rust, and also C++ for that matter, can allow you to declare unsigned integers. That's what I thought too, but LLVM intermediate representation is similar to WebAssembly in this case. It does not differentiate between signed and unsigned integers. So the format of an integer data type is I, and then you specify the number of bits. So it only means that an integer has a specified bit width, not implying anything signed or unsigned. So as a beginner, I wanted to compare it to data types in Rust, but you cannot create any unsigned integers. It is sign agnostic. That is one of the things that trips people up as beginners. So now, having knowledge of data types, we would want to declare variables. So there are two categories of variables in LLVM intermediate representation, and they depend on where in the PC those variables get stored. The first category are virtual registers, which can only be local variables, and then memory variables, which can either be global or local variables. Virtual registers are immutable via the single static assignment property, so they can only be assigned at their declaration. And they are generally used for storing temporary R values and also values that don't change. Virtual registers means that although they are variables, they are later mapped to physical registers by the backend, and we don't know what registers they will get mapped to. So an interesting point is that you shouldn't create too many of these variables, because you might run out of physical registers during register allocation at the backend on a register poor machine. And the syntax for specifying register variable, you just have %, then the name of the variable, and then some value. So some value can only be the return value of an instruction. So this is another common thing that really trips beginners up. You might want to initialize a virtual register with an integer literal, such as the first line, var equals i32.5. You want to assign a 32-bit integer into it. But yeah, it's actually not allowed because of the first rule in LLVM intermediate representation. The only way you can get values are via the return of instructions. So you explicitly have to have the add instruction to generate you a corresponding integer literal. So another note useful for beginners is that if you ever encountered Python before, LLVM intermediate representation syntax of variables is similar in that the variable takes on the data type of the value on the right-hand side. So it's not like in C++ where you explicitly put the data type on the left-hand side. And then, so that was for virtual registers. The second type of variables are memory variables. And these variables are mutable because they are stored in the memory. So unlike virtual registers, they are used for storing L values or variables that must be addressable. So the actual variable itself is considered as a pointer to that allocated memory location, which means that explicit use of load and store instruction is required to access. So, for example, global variables which live in the global section of memory must always be initialized. So we have a syntax of a global variable right here. So you can explicitly initialize them, unlike virtual registers. And then for local variables, we must remember that A common feature of CPU architectures is that allocated memory on the stack is always uninitialized. So you would use alloca instruction to allocate a variable on the stack. The name alloca comes from the alloca function in C, which performs a similar task. But however, this is a built-in instruction. And you should never return the result of a locally allocated variable from a function. So here, %var, it is the pointer. And that would be the same as returning the address of a local variable. But that basically, an interesting point to note is that allocated variables on the stack, they are automatically wiped out when that function returns. So that variable has already been deallocated when the activation record of the executed function is popped off the stack. So that's why you should not return the pointer to allocated the location in the stack memory. That's a common bug that beginners have. So then, now that we know what kinds of variables we can create, we need to know what are the naming conventions. So global names are used both for functions, declarations, and definitions, and global variables. So global names start with the @ sign, and local names, they start with %sign. So they're used both for local variables, so both for virtual registers and for locally allocated memory variables, which are pointers to that variable. So there are two flavors of names. The first ones are unnamed, such as %1, %2, %3, and then we can have also named variables. If function parameters are not and labels are not unnamed, they are given an implicit numerical name. So here the first label is actually %0. So because the name of the label to the entry basic block was not defined, it was automatically given the name %0. The numbered names start from %0 and keep incrementing. Here we see a call to factorial function. So it would be an error to pass either into %0 into any function, because that would mean passing in a label. So that's another common mistake that beginners might have, is that you're passing in %0. You might think that it's a variable. However, it is actually the implicitly named label. Another interesting fact is that we have differences in naming conventions. Apparently, the LLVM intermediate representation allows you to name variables and name variables and labels with the names of instructions, such as the code example on the left. So apparently, it's not a conflict though, because unlike instructions, your variables and labels start with @ sign or a %sign. So there is no ambiguity here between add, for example, and %add. Add corresponds to an instruction.
Hello? Can you guys
In
hear?
LLVM intermediate representation, another interesting thing I found, you can put a dot anywhere into the names of variables and labels. Unlike in C++, there is no member access operator, so the dot is actually a legal character to have inside of names. Since it is not a reserved character, it is not used for anything inside the LLVM intermediate representation, so we can have dots freely in our variable names. So if you click on this link identifiers, it gives you more information about the different naming conventions. So that's what I found interesting. Another thing is that you can actually have both global variables and local variables with the same name, provided that they one is a global variable and the other is local variable, because the prefix character, either a percent or an @ sign, is enough to distinguish them as two different variable names. So here we declare the variables, and when we use these two variables, @a refers to the global variable and %a refers to the local variable. So we can use them both together, and there is no ambiguity. So now we are going to go over the algorithm that is used for naming variables in LLVM intermediate representation. The LLVM compiler, or the assembler rather,
Hey, Constantine, I think we are losing the audio intermittently. We are not sure if it's the mic.
I'm sorry, I didn't hear what you said.
No, we are losing the audio intermittently for some reason. Not sure if it's your mic or something. Uh, just now it
Well,
again. Can you hear us? Okay.
yes, I can.
Okay. Yeah.
So yeah,
Yeah.
so
Keep going.
I'm okay. Yeah, so yeah, so here in this code snippet, we know that %0 is the name of the implicit label of the entry basic block. Since there is no %1, but there is a %2 and a %3, the consecutive numbers property has been broken. This is the error that happens if you would attempt to compile or assemble this code. It says your instruction was expected to be numbered %1. So it's because the variables need to be numbered consequentially. It is not enough to just have various numbered names. They also have to be declared in increasing order. So here's a common question. If, for example, we declare checkbox under the %1. So that actually would not be allowed because it is not enough for all unnamed variables to simply have a final arrangement of consecutive numbers. They also have to be declared in increasing order. So here, looking at this code, in this example, we have used all names from 0 through 4. What could go wrong? We have %0, which is the implicit label declaration. We have a variable named %1, %2, %3, %4. Now we might be thinking, okay, we have all consecutive numbers, so we're good. But unfortunately, it will be an error. So the assembler follows a very simple algorithm to determine if unnamed variables are not correctly numbered or not. So it reads the source code text from top to bottom, maintaining a counter starting at 0. So it says in each line, if the variable number is equal to the counter, it increments the counter and goes on to the next line. So in the first line, it sets its counter to be 0, it checks. Is the variable number equal to the counter? Yes, it is. Good. Increment counter, go to next line. Now it checks. Is the variable number equal to the counter? No, it is not. So it displays an error and it exits. It stops parsing your program. So that's just an interesting thing to keep in mind, is that this algorithm is used by the assembler to specifically enforce the variables to be not only have a final arrangement of consecutive numbers, but they also have to be declared in decreasing order. Another important thing about variables is that we can have definitions of variables and uses of variables. So each variable can have 0 or many uses. So in this diagram,
Is anyone else having
Yeah, I
audio
can't
problem?
hear him. I think we lost.
Okay.
Uh,
Okay.
remove.
Hello.
Oh,
Can you hear us?
yes.
Yeah, I think we lost the audio again briefly.
Oh, sorry.
Yeah.
Yes, so I just said that if a variable is not used anywhere in the program, then it is not needed. So we can access the list of users for any definition. And if a variable is not used anywhere, this will be an empty list. So if, for example, you want to rename %sum or replace it with a different virtual register, you would have to update all of its uses.
Hey, Constantine, I have a question. So,
yes.
Can you go to the last slide?
Last slide, yes.
So, does anyone know if I have to remove, let's say, some instruction in between? Let's say I have %0, %1, %2, %3, and I have to remove %2 instruction. So, do I have to renumber all the instruction after that, or is there some hack where I can just assign %2 to some dummy instruction?
Yeah, you don't need to change the numbers all over. If you're removing something, all it have to be is in the increasing order.
Yeah, but isn't there any way just to, rather than to remove whole instruction, I just assign %2 to some equal to some no operation kind of thing, something like that?
You might. I don't know off the top of my head a total list of all instructions, but you could. So, if I understand your question, Karshad, if you're saying if we have a sequentially a list of numbered instructions and we want to delete one instruction in the middle, well, all the rest of the instructions have to be renamed to comply with the assembler's naming algorithm. So yes, probably replacing everything to the right of the equal sign and having it some dummy, like add iterate to 0, comma 0. So you would just assign a 0 variable to that instruction, because otherwise you would have to rename all the instructions following that, which might be computationally expensive depending on what kind of function you are having.
No, but I think we need to renumber because that %2 might be used in some other instructions, right?
Yes. So for the basic point of it is that if, for example, this percent sum is used in other instructions, and we want to remove that instruction. Basically, we can only remove an instruction if that variable is not used anywhere else in the program, and if its definition does not have any side effects, such as, for example, calling functions, then it can be removed. Because
I understand.
Yeah, what if a function that it's calling updates a global variable, but that percent sum is not used anywhere? Well, we could say, yeah, we can remove that variable, but if its declaration has any side effects, then we could not remove that variable. So, although I have not tried it, but I have studied, and it seems that Clang or LLVM compiler provides us with a list of uses for any definition. If the variable is not used anywhere, this will be an empty list. And if you want to, for example, rename a percent sum or replace it with a different virtual register, you would have to update all of its uses everywhere that instruction is that virtual register is used.
Yeah, I understand.
Yeah, so we would use data flow analysis, which means finding where that variable / value is used and by which instructions or variables. So the compiler or the assembler takes this information to generate a domination tree from the control flow graph to determine if the variable uses are valid. So here on the right side, I've just drawn the domination tree. It's like a tree with nodes inside of it. So a parent node in the tree, which is the declaration in this case, is called the dominator. In simple words, we can think of it as executing the source code along different paths. So for example, here, a bug in which we have a use preceding its definition. So the assembler complains that the instruction does not dominate all uses. What does it mean, does not dominate all uses? It is not a dominator node, means that if it dominates all uses, it is a dominator node. It means that it is a parent node and it has a way of reaching all its possible uses. If it does not dominate all uses, then one of these links is cut. So the tree is broken. You will have unreachable nodes. So nothing can be used before it is defined or declared temporarily, not spatially. By temporarily, I mean regarding time, and spatially means regarding space. So it means that all variable definitions must be reached at an earlier point in time in the program's execution than the variable's uses. It is a common misconception to think that this statement means that all definitions of variables have to be spatially above in the source code than their uses. Although this is not the case, it simply means that all variable definitions must be reached at an earlier point in time in the program's execution than the variable's uses. So,
Hey, Constant, quick time check since it's 1 o'clock and you have some more material to go over, maybe we can continue in the next round back.
Can I go over this last slide though?
Yeah, sure.
Okay.
Quickly check. Okay, thanks.
So this is an interesting property that I discovered while I was researching, is that there is such a concept as temporal versus spatial declarations of variables. Spatial means relating to the visual organization of the source code text, such as when you just look at it with your eyes, which lines are above or below. And temporal means relating to the running time of the program, so which statements are executed in what order. So because programs can have control flow among different basic blocks, the order in which the declarations are reached is non-linear. So the rule that all uses must be reachable from their definition applies to definitions of variables during the running time of a program, so spatially. Temporarily. So say for instance you jump from a basic block located lower in the source code to a basic block located above it in the source code. Although it might seem at first that this rule might be violated because we are using %2 above its definition. Remember, since the definition of %2 gets executed first, the use of %2 is temporally later. Therefore, its rule is not broken because we first go to this basic block. First, we declare the variable %2, then, only then we use it. So the algorithm checking the reachability of uses from their definitions, which is the dominator tree algorithm, thinks temporally, so in terms of time, in terms of the program's execution. But the LLVM intermediate representation naming algorithm, the number naming algorithm thinks spatially. So it reads source code line by line from top to bottom. And that is why the name %2 has to be spatially below %1. But for constructing a dominator tree and checking if the use of a variable is valid, we are thinking temporally. So this is actually a valid dominator tree, because if you would grab it by the dominator node and leave it hanging like a pendulum, it would unfold and be hanging down. So it is a valid dominator tree. So don't let this confuse you as it's jumping up and down. It's valid dominator tree. So this was the last slide about temporal versus spatial declarations of variables, which concludes this first section, which is everything to declare variables and all the various intricacies, various questions that might result in that. We are taking a look at how do we access variables defined in memory. We do that by using load instruction and store instruction. Load instruction means loading the data from the random access memory into the CPU, reading from memory into a register. And store instruction means storing register values from the CPU into the random access memory. So writing from a register to memory. Consider this. We are allocating a 32-bit integer on the stack, and we are returning the starting address of that memory, of that allocated variable in the stack into that a pointer variable. Now we want to store something into the variable pointed to by ptr variable. So we store 32-bit integer value 3 into this pointer. And on the next line, we load a 32-bit integer value out of the 32-bit pointer, the memory location pointed to by this pointer value. And if you were to print %val, you would indeed see that it is a 3. So just visually looking at these instructions, we see that load returns a value and store does not return a value. It's a common question in beginners. Why load returns something in LLVM intermediate representation while store doesn't return anything? So, unlike in x64 assembly, instructions in LLVM IR do not specify destinations. They just return the value, which is assigned into a variable, just like in C, C++. For example, add does not add into. It just adds two values and returns the result as R value, allowing the program to assign that result to whatever variable they want. Load instruction also loads a memory from a value from a memory location, and it returns that R value, allowing us to assign it into a variable. It is not a load into operation. So LLVM intermediate representation instructions values like add and load do not specify a destination operand for the flexibility of assigning that R value into a virtual register. Now, why is that? It is because, unlike in x64 assembly, which has actual physical registers, because LLVM intermediate representation does not have actual registers, it cannot specify a destination operand because the destination doesn't exist. Like, we don't know which register it will get assigned to finally, because register allocation is performed by the back end. The LLVM intermediate representation doesn't even know about which physical registers the virtual registers will get mapped to. Hence, it allows the programmer to freely assign R values into virtual registers. And because there is an infinite number of them, they are treated similar to variables in C or C++, allowing us to use a flexible assignment operator syntax for assigning them, as we see in the load instruction. Now, the store instruction doesn't return anything because it already has a provided destination as an operand. And that destination is the memory location of the pointer. That's a uniquely identifiable location. And since it knows where to store the value into, it doesn't need to return anything. Think about it. What would the store instruction return? It doesn't make sense, right? It's not returning an R value or anything as a result of a computation or memory access. Here is a common beginner's mistake that people make. An important point is that you cannot use the values in memory objects by directly accessing the pointer or trying to dereference it in line as in C. How in C programming language we are used to writing large complicated expressions and dereferencing the pointer in line. Well, that doesn't work. You must load the value into a virtual register first. To illustrate this concept, I have this example. I'm declaring a global variable. It's a 32-bit integer with the initial value of 20. This gets stored into the global variables section of the memory, and the pointer to that is returned and assigned into this @x. Now you might be thinking, if, for example, I have an integer with the value of 8, with the value of 4, I want to add 4 to 20 and return the result. You might be thinking, all right, I'm adding this I32 value @x and adding it to %a. However, you can't do that because the error that the LLVM assembler emits is a global variable reference must have a pointer type. So this @x is actually a pointer to the globally allocated variable, which is why you can't do I32 right here. You have to explicitly dereference the pointer before doing that. All right, you may say, easy to solve this problem. add the star here, and I should be good, right? No. Now the problem is %A defined with type I32, but expected an I32 pointer, because the add instruction expects both operands to be the same data type. If we specify the I32 pointer at X, this also has to be a pointer, but it is an integer, so it thinks you're trying to add two pointer values together. So one does not simply dereference a pointer variable in line in LLVM intermediate representation. So what you do is you load into a temporary virtual register first before you can use the value stored at that memory location. So this reads as I'm loading a 32-bit value from an I32 pointer at X, and only then I can use that value. So every time you want to access a variable allocated in memory, such as a global variable or a local stack allocated variable, you always need to use load and store. Now, a question that I had when studying was, does LLVM intermediate representation support direct memory to memory operations, or do you have to load everything into virtual registers first before performing the operations? So I asked Mr. Scott Pillow, and he answered me that in general you do have to use load and do the operations in virtual registers and then do a store. So all the input-output operations will be explicit as compared to C, for example, where it may not be obvious when memory is being accessed. But there are intrinsics such as LLVM memcopy that lets you copy from one memory location to another without having to go through virtual registers. But I won't be covering this topic today. So that's